Hey everybody, the photoelectric effect is an amazing idea in physics that's changed the way we get energy in the 21st century. In today's video, I'm going to show you a real example of the photoelectric effect working in the lab, and then we'll explain this phenomenon step by step, ultimately giving you a better understanding of why Albert Einstein earned a Nobel Prize for his explanation. Thanks for tuning in, and I can't wait to learn with you.
What's up, everybody? Welcome to Neil's not so boring world of chemistry. Let's go into the lab and take a deeper look.
This is an electroscope, and I'm going to use it to demonstrate the photoelectric effect. It's a neutral object, and you can see in the diagram that it has the same number of positive and negative charges. Here I'm adding extra electrons to this gray rod, and watch what happens as I touch the rod to the top of the electroscope. The needle in the center is moving because now it's repelled from the main post. You see, I put extra electrons into the electroscope. I charged it. And now those extra electrons are causing this repulsion that you see demonstrated by the needle. Now it's interesting to note that there's visible light shining on the electroscope, and yet the needle will stay repelled. You see, in the photoelectric effect, light is supposed to be able to knock electrons out of metal devices like the electroscope. Why isn't it happening? Well, let's try a different type of light. This is a UV lamp, and as I turn it on, watch the needle. And there it is. The needle has moved back in line with the main post because, as you can see in the diagram, the electrons were kicked out by this particular type of light. And that is what the photoelectric effect does.
So in summary, what we just saw in the lab was the following. The photoelectric effect is a method by which electrons can be pushed out of metal atoms using light. Experimentation shows that it's not just any light, and there's even more. Depending on the metal, the type of light required to get the photoelectric effect to work changes. If you look on the board behind me, you'll see two different examples of sodium metal. Now, when we shine longer wavelength light on the metal, we notice that no electrons are pushed out. We don't get the photoelectric effect. On the other hand, if we decrease the wavelength from 714 nanometers to 419, we do see electrons moving out of the metal surface. It turns out that for each individual metal, there's a particular wavelength and frequency of light that you need to have the photoelectric effect happen. Now, this is an amazing discovery in physics, and again explains how solar panels work and how we can generate electricity using the sun. But this also posed a really significant problem for our understanding of light. And in the next segment, we're going to look at how this shifted and changed the entire way we conceptualize what light actually is.
The physicist Thomas Young had developed a well-respected model of light, wherein light was represented as a continuous wave of energy. There was a problem, though. Young's model failed to explain certain experimental outcomes regarding the photoelectric effect. Now, there were many problems, but I'm going to focus on just one. Let's take a look at this lamp, which is pointed at a piece of sodium metal. Now, I'm going to begin by turning the lamp on. And here we see that it's emitting a red color of light. And you can see the wavelength is about 720 nanometers. Now, the photoelectric effect doesn't seem to be happening here. There are no electrons leaving the piece of sodium, and that's not surprising considering that in the last segment we talked about how each individual metal has a minimum threshold energy or a specific type of light that gets the photoelectric effect started. So if I take this slider and I start to shorten the wavelength, in other words, increase the frequency and energy of this light, I will eventually get to a place where electrons start to move and the photoelectric effect is happening and working. Now, here's where Young's model ran into an issue. You see, if I lower this light back down to that longer wavelength red light, Young's continuous wave model suggests that even though electrons are not being ejected now, if we just leave this light shining on the piece of metal for long enough, Eventually, that continuous flow of energy will build up in the sodium metal, and eventually there will be enough energy to get the electrons moving. But no matter how long we leave this red light on, we are not going to see any electrons leaving the metal surface. Now, I'm not going to leave the simulation running for minutes and hours, but trust me, if you'd like, you can try it on your own time. The photoelectric effect doesn't happen, and this puts Young's model into question.
In order to resolve the issues and confusion around the photoelectric effect that we just saw in the last segment, Albert Einstein steps into the picture, and he introduces a revolutionary idea. Light was previously thought of as being a wave, but Einstein suggests maybe it has wave and particle-like properties. And in certain experiments, like in the photoelectric effect, both of them are on full display. On the one hand, the light has frequency, wavelength, and energy, and they're interconnected. But on the other hand, Einstein introduces this particle concept by using the word photons. He asks us to imagine that light is comprised of smaller packets of energy, each one of them being a photon. And when we turn up the brightness of a light, what we're actually doing is releasing more of these photons, more of these little pieces of light energy. And each one of them can knock into or push out one single electron. So in experiments where the brightness of the light is dim, we don't see a lot of electrons leaving, maybe just a few. But if we then turn up the brightness, we're releasing more photons, and each one of them can interact with an electron, so we see more electrons being pushed out of the metal. And this is how we now think about light in the 21st century. It's not just a wave, it's not just a particle, but in fact, in the photoelectric effect, we see it behaving as both.